All right, welcome back, everyone. Let's continue our conversation on beam deflection. And in this video, what we're going to look at is instead of developing an equation for the elastic curve, because there's a lot of common loading scenarios, we can just look it up in a table. So these are the tables we're going to be concerned with today, and these are found in the Hibbler textbook or in Blackboard under the textbook images folder or in the textbook images folder. And you can see there's basically, zoom out a little bit, there are 2 pages. I consolidated these into a Microsoft Word document consisting of 2 pages. The first page is simply supported beams, so I have a support on each side, and the second page are all cantilevered beams. So when you're trying to figure out your type of load, you can look at that. Now, to use these tables, you have to be careful because the different columns are important. The first one, slope, well, we talked about slope, that's your theta. However, notice this is theta max because theta is constantly changing. The only one thing we'd probably care about is theta at the very end. The big issue here with this section that I've seen in the past is the difference between deflection and elastic curve. Remember what elastic curve is, or the elastic curve, it is the deflection. It's an equation for the deflection along the length of the curve. The difference between that and just saying deflection is at one particular spot. So this might say V max. So V max in this loading only happens at one place. It happens right at the center, it looks like. And so the only way you can use this equation is if you're looking for the maximum at the center of that beam. However, if I wanted to know the deflection at some distance over from one side or the other, I would have to use the elastic curve equation and sub in, whatever x value that is. Now, by the way, if this were, say it's like a 6-meter beam and this were 4 meters over, I cannot just put 4 in there. The reason being is because if I look down here, it's saying, well, x has to be between on this one half of the beam. However, there's nothing saying that I can't, in essence, make my axis the opposite direction and say if this were a 6-meter beam and I wanted to know 4 meters over, I'd work the other way and say, well, I want to know at x equal 2 meters, plug it into that equation, and I will have my deflection at that location. So that's a little bit on how you can use these curves. You have to think about what everything is saying as far as what location, deflection versus elastic curve, and that kind of stuff, right? So the other thing I want to say about these tables is that we can actually use that concept of superposition with these tables. And if you don't remember what superposition is, it's basically saying that we can break things apart and add them up in parts and pieces. So for instance, if I had a beam that was cantilevered out and this beam had a distributed load over, say, half of it, and then I had another load up here, if I were to look in the table under my cantilever beams, I do not have that load scenario, right? I do have it with point load at the end, even though it's going the opposite direction, and I have it cantilevered over half, but I don't have them together. What I could do is say that this is the same as breaking it into 2 parts and looking at the deflection of each part separately. So I could look at the deflection from this distributed load over half the beam, and I can imagine what my deflected shape looks like. It would be something like that, where I have, I'm going to call that D1 for my displacement at the end of the beam, and I can add to that the displacement due to that point load. And because this point load is pointing up, my deflection will go up, and I end up with D2. So my total deflection at the end of the beam would be equal to D2 minus D1. So let's take a look at an example of how I would put all this together using these tables. So for this example 1, we're given that we have a simply supported beam 3 meters long, and we have a distributed load across the entire beam of 2 kilonewtons per meter. We have a point load of 4 kilonewtons acting at 2 meters from the left-hand side, and we're asked to find the maximum deflection. So I am going to break this into two loads, one for the distributed and one for the point load. So I'm calling these two loads 1 and 2, 1 for the distributed load of 2 kilonewtons per meter and 2 for the 4 kilonewton point load. And when I break it apart, now I can find those two loads in the table and find my deflection. So going back over to these tables, the first one I'm looking at is a distributed load over the entire section, right? So here's what really gets a lot of people is what I'm looking for this problem is the maximum deflection on this beam. And you'd think this would be great. I have it right here. V max for distributed load is minus 5 WL to the fourth over 384 EI. Unfortunately, that doesn't work. The reason that doesn't work is because where is this occurring? This is occurring at the very midpoint of that beam, right? Well, is that where our deflection is actually occurring? And it is not. Because we have a separate point load on our beam, we know the actual location. I mean, we don't know where it is exactly, but we know it's going to be shifted slightly over to the right. So we want to know our maximum deflection would be somewhat skewed where it isn't quite symmetric but more weighted towards the right hand side due to that point load. So I can't use that equation. Instead, I'm going to use my elastic curve equation. Since I don't know where this is occurring, I'm going to have to find out where it's occurring later. But so let's start by using this elastic curve equation and plugging in everything that we know for that side. So there's the equation, just copied straight over from the table. Probably wouldn't waste my time normally, but you know. I have a load of 2. I'm just going to leave all my units the way they are with kilonewtons and meters for right now. And then this x remains a variable divided by 24 EI. Once again, I don't know what EI is, so I'll just leave it in variable of EI at this point. My L is the length of the beam, which is 3, so 2 times 3 is 6. And 3 cubed is 27. So for the other side, for side 2, it's the same idea. Now we're saying we have a point load that is non-centered, so we're looking at this part right here, right? I can't use this top one because that says it's right in the middle. Well, our load is off-centered slightly. It does say that we have a deflection at x equals a. Can we say that? No, we can't say that either. It's not necessarily right below the point load because the distributed load is affecting it. So instead, once again, we need to go to this elastic curve equation. Now it says that this deflection would occur between 0 and a, and that does seem to be like it would be valid and it would hold up. Yeah. So I'm going to start by copying that equation back over here for my point load. And now I can plug in those variables that I have. The load is 4. B is my distance. If I were to go back and look at the table, B is my distance from that right-hand side. So that is 1. X, once again, is a variable. I have 6 EI, and then 3 is the total length of the beam. Plugging everything else and simplifying, I ended up with minus 2x over 9 EI times 8 minus x squared. Now what we said is I broke them apart. Now I want to add the whole thing together to find my elastic curve equation for this loading scenario. So then I'm going to add this V1 and V2 together. When I do this, let's go ahead and just factor out that EI value. So all I've done at this point is factor out EI, put the two equations that I have together, and from here it's some algebra to multiply through so I can add my like terms. And it was just some algebra, so I think maybe if you want to follow along or want to double check my algebra, I'd hit pause and go through the steps. But otherwise, you could trust me. This is what I ended up at the very end for my equation for the elastic curve or the deflection of this beam. Now, once I have the equation for the elastic curve, that's not what it was asking for. It says, what is the maximum deflection, right? So how am I going to get the maximum deflection? Well, if I have the equation for a line, I know the maximum will happen at an inflection point, or what I can do is take the derivative and set it equal to 0. So that's what I'm saying there. If I need my maximum deflection, I know the derivative of the elastic curve with respect to x is the same thing as theta, must be equal to 0. So let's start by taking the derivative of this nonsense. The 1 over 36 EI is a constant. And then I end up with this minus 12x cubed plus 78 x squared minus 145. Just taking the derivative of this whole thing there, right? Oh, awful, awful. And once I have the derivative of that, I can set it equal to 0. Solve for x. It's a little ugly. I just put it in my calculator, and I got x is equal to 1.5647, carrying a lot of digits, meters. So it's a good time to double check. Like, so is it at the midpoint? No, the midpoint would be 1.5. That's why I can't use that equation. Is it indeed between this end and this point load? Because that was an assumption we had to make to use this equation, and it is, because that means it have to be less than 2, and it is. It's 1.5647. So the last step is to plug it in, and I can say that then the deflection maximum is when I plug that x in to that equation. Now I just did it all once again in my calculator, so you might want to double check this. But I got minus 4.035 kilonewton meters cubed over EI. So that's a basic example on how you would use something like this. I do want to say one thing that'll help a lot with the homework. I call this a table trick, or another way that you may want to manipulate the table. And that is for a cantilevered beam that is on the second half of the beam, or distributed load that's only on the second half of the beam. So let's say I had something like this, 5 kips per foot or something, and I knew that these lengths were 2 5-foot sections, or a 10-foot cantilevered beam. Well, if I come over here to my cantilevered beams and look at a distributed load, that does not exist. I do not have that. I do have this one, but the problem is if I look at the distributed load is on the side closest to the wall. Well, I have the opposite, where the distributed load's on the opposite side. It's over here, right? So one way that I can do this is I can say that this is the same thing as a distributed load across the entire section, and then what I would do is I would add on the reciprocal of, or the opposite direction for that first half, and that would leave me with just a load pointing down on the second half. So when you get to the homework, it's almost identical to that problem. The only difference is on the homework, I gave you one additional load, right? So on the homework, when you get there, say I did have yet another additional load up here. I didn't plan on doing this, but let's say this was 6 kips. I could add just another one in here and say plus a cantilevered beam with a force in the middle of 6 kips. And then you'd have 3 terms you're adding together for the elastic curve. And I believe that one was looking at the elastic curve at the very end of the beam. And in that case, you could use Vmax for every one of those. Well, actually, this one, do we have one for the midpoint cantilever? Yes, we still have a Vmax. So you could use Vmax for that one. So take a look at that homework. Let me know if you have any questions or comments, and I'll talk to y'all later. Thanks.